Now, an interesting question. How does a router set forwarding table entry to a distant prefix? Recall our previous example, and that 1A, 1B, 1C within the AS1 learned about destination X via IBGP from 1C. 1C tells 1D that the path to X goes through 1C. But how does 1D reach 1C? This is decided by OSPF intra-domain routing, telling how to get to 1C through forwarding over outgoing local interface 1. So, the result of inter-AS and intra-AS routing together translates to writing the interface to take towards a final external destination. With a similar procedure at 1A, it knows 1C is used to reach final destination X. OSPF intra-domain routing tells it how to get to 1C, which is through interface 2. Note that a router may learn about more than one route to destination AS. As we saw in the previous example, AS1 learning about different paths to X through AS2, AS3X, or only AS3X. The router may select a route among the ones it learns in different ways, based on the attributes we discussed. It might select it based on local preference value, which is a policy decision. It might choose the vector with the lowest number of ASs within the path vector. It might choose the closest next hop router that reaches that destination. This is called hot potato routing. Or it might choose based on different or combination of parameters. In hot potato routing, the router chooses the closest next hop router that reaches that destination. For example, in this figure, router 2D learns via IBGP that it can route to external destination X using either of 2A or 2C. If it chooses the local gateway that has the least intra-domain cost, it will pick 2A, because the cost of link to 2A is 201, which is less than 263 to 2C. This is called hot potato routing. Note that this has resulted in a longer AS path. As we previously discussed, BGP can enforce policies. Using policies, ISPs can control their traffic. For example, suppose we have the following network with A, B, and C provider networks and W, X, and Y being customer networks. A advertises path AW to both of B and C, but B does not want to route C's traffic to A or W. This might be because there is no revenue in doing that, or for security reasons. This could be achieved by B not advertising BAW to C. C will never learn about a path CBAW to destination W. It will always route CAW, not using B to get to W. In the same network, X is dual homed, meaning it has two networks it is getting service from, B and C. X may not want to route the traffic from B to C. To achieve this, it will not advertise to B that it has a route to C.